Hello everyone, I am Yizhong Zhang from Microsoft Research Asia. Today I will present our work, RemoteTouch, Enhancing Immersive 3D Video Communication with Hand Touch. Social touch is important in human society. Touch is an efficient and powerful way for people to express emotion, especially for people in close relationships. Immersive video communication has decreased the distance between users. By displaying life-size portrait images on big screens, users can feel that the remote user is sitting there, talking to him in person, as if they were in the same room. These systems try to emulate the experience that users talking to each other through a window. Our goal is to enable hand touch capability. Specifically, we want to provide user a consistent visual and physical experience during the hand touch, as if they are only separated by a transparent glass. Our work is based on immersive 3D video communication and also related to hand tracking and rendering in remote collaboration, social touch in VR and AR, and haptic rendering. State-of-the-art 3D video communication systems has enabled real-time view synthesis with frontal view cameras. By capturing images from source view cameras on the screen boundary, the portrait image can be synthesized from the view behind the screen. As the position of the virtual target view can be controlled to align with the eye position of the remote user, eye contact between users can be preserved. This is an advantage over fixed physical camera behind the screen. However, the key challenge of synthesized portrait image is that when the hand is close to or touched to the screen, the source view cameras cannot see the hand, especially the palm region, resulting in the hand missing in the synthesized portrait image at target view. The key idea of our work to solve this problem is a dual representation for hand rendering. We synthesize the portrait image using the method proposed in VirtualQ. At the same time, we track the motion of hand in 3D space and render the hand mesh. We also proposed a distance-based fusion method to fuse these two images together to obtain the portrait image for display. So the hand is visible throughout the touch process. This is the hardware setup to achieve hand touch. We added a leap motion to the VirtualCube system to track the motion of hand in 3D space. The hand skeleton drives the deformation of the 3D hand mesh. The pose of all cameras, the screen, and the leap motion are calibrated so that the tracked hand coincide with synthesized portrait image. To further enhance the touch experience between two users, we installed a vibration motor on the screen. Once a hand touch is detected between two users, the screen will vibrate to provide tactile feedback to the users. The image-based rendering uses an unstructured lumograph consisting of a geometry proxy and images captured by RGBD cameras. We use a neural network to predict the blending weight of each pixel from source views and compute the portrait image at target view. The image-based rendering only synthesizes regions visible in the RGBD cameras, so when the hand is close to the screen, the palm is no longer visible in the target view image. When the hand is close to the screen and captured by leap motion, 3D geometry-based rendering will begin to take effect. Leap motion tracks the hand skeleton in 3D space, drive the motion of 3D hand mesh, and render with the same view perspective of the portrait image. As the whole system is calibrated, the rendered hand align with the portrait image naturally. The 3D hand model has predefined texture and scaling weight to a template hand skeleton. For better matching the portrait image, we adapt the shape of the hand model to fit the hand skeleton and adapt the hand texture to fit the portrait image. Finally, we use a distance-based fusion scheme to blend the portrait and the 3D hand into one image. As the hand reaches to the screen, the hand in the image-based rendering will become blurred and finally disappear, while the 3D hand will appear as soon as it is detected by the motion. Therefore, there is a range that hand exists in both image-based and 3D geometry-based rendering. For a smooth and seamless visual effect, the blending weight of 3D geometry-based rendering increases as the hand gets closer to the screen. We tested the dual representation of hands with diverse users and proved that our shape and appearance fitting scheme is robust to different skin tones. This demo shows the scenario of hand touch between two users and how haptic feedback enhanced the touch experience.
Hi Jack, long time no see. Hi Tom, long time no see. You look great.
As you can see, both users feel the successful high five as a vibration of the screen. If the two persons' hands do not match, the touch is not successful and it will not trigger a screen vibration.
Long time no see. You look great.
To evaluate the effectiveness of our system, we invited 26 users to try our system and provide feedback. Almost all of them appreciate the visual effect of hand approaching process and agreed that the touch experience decreased the mental distance between remote users. They also thought that the vibration made the hand clapping more attractive. To conclude our work, we present a method to enhance the immersive experience by adding hand touch capability to a large screen video communication system to make users feel that they were only separated by a transparent glass. We proposed a dual representation and distance-based fusion approach for realistic hand visualization of the approaching process. Finally, we emulate hand touch with haptic feedback by screen vibration and verified the effectiveness through user experience test. For future work, we will continue improving the hand tracking accuracy and hand fusion quality. Currently, we placed a leap motion in front of the screen for hand tracking. It is interesting to design more compact and integrated hardware for hand tracking. We also would like to try more kinds of feedback for better user experience. This is the end of the presentation. Thank you.